Thank you for the introduction. I thank the committee for the award. That really honors me. Hope my talk will not disappoint. So I'm going to talk about these wonderful things called nominal recursors. And I'm going to dedicate really most of my talk to explaining what these are, culminating with a more abstract view. But let me start with a bit of motivation. I work on building proof-assistant infrastructure, definitional and proof mechanisms. And most of us who have used a proof assistant for formalization know how important it is to start off with the right foot when doing definitions. So we need to get the definition at the proper level of abstraction, and ideally in a hassle-free manner. Sometimes these two goals can be a bit antagonistic, but unless we get the definition at the proper level of abstraction that matches our intuition, we're going to struggle later on when doing the proofs and when doing the interesting bits, when developing the meta theory. So in this talk, I'm going to focus on a particular piece of infrastructure that I think it's very useful for many of the meta-theoretical results that we're developing at POPL, many of the syntactic translations and interpretations that the researchers are developing. And I'm going to focus on recursion principles for syntax with bindings. In other words, recursion principles that are aware of the bindings and respect the binding structure. They pay their respect to the binding structure. And the main character of this talk will be the syntax of the lambda-calculus. So these are the only notations that I will kindly ask you to remember. So please stay with me on this slide. The lambda-calculus syntax is specified by this grammar. So we have the lambda terms. I will just refer to them as terms. And the grammar says that a term is either a variable, or rather an injection of a variable, or an application of two terms, or a lambda abstraction of a variable in a term. You can see the more familiar notation there, but I'm going to use this more pedantic notation. I'm going to use these operators VR, Epi, AP, and LM. So terms, and this is very important, and this is people working on syntax with bindings know that this is sort of the source of all major difficulties. Terms are equated or identified modulo alpha equivalents. So essentially the bound variables do not affect the identity of a term. So for example, lambda xx is the same as lambda yy, which effectively means that lambda is not a free constructor. Okay, a brief parenthesis here. So I'm going to focus on the nominal approach, and one of the things that I like about this approach is that it does not start by encoding away, by correcting the informal definitions, but rather goes along with this informal definition and tries to make sense of them. So we have the lambda constructor is an actual operator that takes explicitly a variable and a term and returns the abstracted term. And a prominent variant of the nominal approach is nominal logic by Gaba and Pitts. But there are other mainstream approaches as well. So just to put them here briefly for comparison, there is the nameless or the Brown approach, where the bound variables do not exist, but a fixed position is being bound. And then we have the higher order abstract syntax approach that borrows the bindings from the meta level. So the way that these representations proceed actually has deep consequences in terms of the reasoning principles. I'm going to focus, as I said, on nominal recursion principles. Recursion principles for syntax with bindings within the nominal approach. Now, let me get a little more pedantic about terms. So these are the terms that I introduced before, the lambda terms. And we have this lambda that is not a free constructor. What does it mean? What does it really mean that they are equated modulo alpha equivalents? Well, what really happens is that we have the preterms, and I'm going to just use P for the operators on the preterms. These are completely, sometimes they are called raw terms. These are a completely free data type, nothing special about it. And they have term like constructors. And we define alpha equivalents inductively. And then we take the terms to be the quotient of preterms. And then we show that the preterm constructors are compatible with alpha, which allows us to lift the preterm constructor to term constructors. And after we have enough properties proved over terms, we can completely forget about preterms and focus on the terms. So we can work at that abstraction level. Now, this may look a bit tedious, but this is perfectly standard and fully automatable. These are polytypic constructions. So, and they have been automated in definitional packages such as Isabelle nominal. So this is perfectly standard and can be fully automated. Okay, so let's delve into what a nominal recursor is. So let's consider this Knox operator that takes a term and a variable and returns the number of free occurrences of that variable in the term. For example, so you see here that term that on the left, how many times does x occur free in it? It's just once, because the left-hand side occurrence is free, whereas the others are bound. So this is what we want to define. So how would we define this in an ideal world, on which, incidentally, we don't live in? Please take 3 seconds of my talk to think about how you would define this. Well, we would write the expected recursive clauses, right? So we just want to traverse the terms recursively, and we show essentially how our function interacts with the constructors. In particular, in the lambda case, we're going to see if our variable is exactly the abstracted variable, and if this is the case, then there's no occurrence, so the number of occurrences is 0. Otherwise, we just export all the occurrences. Okay, so this is what we would normally write, and this is what, for example, Barendrecht in his monograph writes when he defines such operators, even though terms are equated modulo alpha equivalents. So we have a bit of a struggle between the intuition and reason here, trying to reach consensus, because this feels right. This feels like what we want. But on the other hand, if we are pedantic, and we should be when we formalize, the choice of the variable x may influence the definition. So we are not sure that this choice is completely irrelevant. But the intuition still says, well, it feels irrelevant. It feels like this is still the right definition. But this is not trivial. For example, that particular choice of the variable x in the lambda case, when we consider the abstraction, that is explicitly tested for equality with the variable y. So it is not absolutely trivial that the choice of the variable does not matter. And this is where nominal recursion comes in, and it essentially bridges intuition with reason. But it is not a Deux ex machina situation, so it does not just say, okay, this is actually fine, but it says that this can be completed to a definition. And the essence of nominal recursors is in this completion process. So what does it mean to complete this into a rigorous definition? For example, one of the nominal recursors, the most famous one by Gaba and Pitts, considers an extra operator to prop recursion, to further help recursion. So it's not only about the interaction with the constructors, but also about interaction with other operators. In this case, the permutation operator that permutes all the variables in a term according to some function. So if we consider these additional operators and verify some conditions, more about this a bit later, then we are fine. So then this is accepted as a definition. So we get our original definition as a subset of this fully rigorous definition, so to speak. So we don't have to change a representation or to recurse over different constructors. Okay, so let's look at the situation a little bit more abstractly. So let's say we have, first let's look at a completely free data type, the data type of preterms. These are not yet quotiented to alpha equivalents. So let's say that we want to define a function h from preterms to some domain, some target domain A. Now, how the normal recursive definition goes through, essentially how I sketched before. So we're going to ask these questions. How does our intended function structurally interact with the constructors? So we ask what I will call the constructor questions. Now, how do we answer the constructor questions? Well, we need to put some recursive expressions there, but the way to conceptualize this more rigorously is to think that we have operators on the target domain that match the constructors of terms. So these are, I'm going to refer to this as term-like, as constructor-like operators. So we just plug those in as answers. So the answer would just say, well, our function is supposed to commute with the constructors. Okay. So what this really means is that we organize the target domain into a pre-term-like model. So we define operators that have the same hierarchies as the constructors. And this is all. So this for a free data type, we have this definition guaranteed to be correct by the standard recursion theorem for free data types. Now, moving from pre-terms to terms, we ask the same question. We ask the constructor questions, and the first step goes in the same way. So we know what we want to define, so we know how to answer these constructor questions, which means defining operators, constructor-like operators on the target domain. But in order to make this work, we are asking additional operator questions. Like, for example, here, we are asking, how does this intended function interact with permutation? And how does it interact with freshness? Here, we can treat freshness as a predicate. So these are two additional questions that help us that help us get the definition through. So we answer this by thinking about how our hypothetical function, how it is supposed to interact with these operators. And this gives corresponding operators on the target domain. And we have, only now we can have a definition, the definition accepted. So we need additional operators, and we need to check some additional properties. And now nominal recursion guarantees that there exists a unique function satisfying what we normally identify as the inductive, as the recursive clauses, which are 1, 3, together with some bonus properties that forced us to think in advance, essentially, about what we want. So this is really not a waste of time helping this definition go through, because we are talking about some properties that we're going to ask ourselves anyway when we are studying this function. Okay, so just to summarize how a nominal recursor works, we're asking, in addition to the operator questions, we're asking in addition to the constructor question, we're asking some additional operator questions. And for the nominal recursors in the literature, they are all discussed in my paper. These operators, this combination of the operators vary. So we can have permutation, swapping, freshness, renaming, or substitution. And yeah, again, the questions that we ask about them tend to be the natural questions. And here is a piece of magic that I'm not going to justify, but in all the examples that I have seen in the wild, the properties are actually, the properties that need to be checked are often trivial, with a few exceptions. Okay, so let me skip to this other example, and let me just give an abstract view about what's happening here with nominal recursion. So this is a concept of an epi-recursor, which subsumes the nominal recursive example that I gave. So we have a base category and an extended B and an extended category, and we have this is, we can look at this diagram and not necessarily consider the rest. So we have this base category, which contains, corresponds to the usual notion of term or whatever syntactic binding we consider with their constructors. And we have the extension with additional operators that are specific to the specific recursors. And what happens above is that this is where we prop recursion. So we help recursion from above. When we want to define a function recursively from terms to some arbitrary set B, let's say, which is an object in the category B together with constructor-like operators, what we're doing is we get help from above, so to speak. So we extend this algebra, constructor algebra here to an operator algebra, and we use the initiality, which is the recursion theorem in this extended category, and we just take the restriction of this. So R is the forgetful functor that forgets the additional operators that were only used to prop recursion. Okay, so some other things that you can find in my paper. Again, so I hijacked this for just giving a tutorial on nominal recursion, but essentially I show how all the recursors from the literature are Epi-Recursors in the sense that I just described. And you can create new ones by cross-pollinating existing ones, and you have the an expressiveness hierarchy that discusses how the different operators fare relatively to each other. And I also studied the nominal corecursor, which are in some sense dual to nominal recursor, in others they are not. And I thank you for your attention, and also I thank the people who have introduced the nominal recursors and corecursors. We have the corecursors at the bottom. All right. Thank you. Thank you.
Hi, thanks for the talk. The kind of naive question for type theorists when you see something like this is to think this is a special case of some sort of quotient inductive type or something like this.
Yes.
Is there any relation? Is this? I mean, I know that there has been quite some work on trying to find semantics or this kind of stuff for these kind of non-free inductive types. Is this related in some way?
Yeah, absolutely. This is related to quotient inductive types, and this is actually related to something that predates quotient inductive types, which are initial models in Horn theories. So you have a Horn theory given by conditional equations involving predicates as well, and you have some initiality theorems. Some of these recursors fall squarely under that pattern, but of course, I mean, they have their details. Because the alpha equivalency is defined in a specific way, is not defined so that one makes manifest that you are talking about a Horn theory. But other recursors, notably the original nominal recursor, is not in this category because it asks it has some non-equational axioms. So that would be interesting to see how that fits into the type theoretic framework, whether those types of non-equational axioms make sense there. But yeah, that's something interesting to look at.
Thank you.
Thank you. So you say that your aim is to combine recursors. Does it mean that you're aiming for some kind of category or two category of recursors so that you can make co-limits of them or something? Is that what you're...
that sounds like fun.
Like rough kind of fun, I would say.
But I'm not, yeah, that would be an interesting sort of theoretical value to explore. So in my case, my motivation was what recursor to use for a definitional package in a proof assistant, and what are the relative advantages of different recursors. How they reduce to each other and so on. So to make the best of all worlds. So some recursors are more expressive than others. You will find this in my paper. But it's not only expressiveness. It's also some are lighter. Some require fewer operators. The infrastructure is sometimes lighter and so on. So there are different criteria there. And I think my conclusion is that I should have them all in a definitional package and reducible to each other. So I guess I could have reached this conclusion without studying.
Thanks.
Last question.
So related to what you just said, is it the best or the best so far? The corecursor or recursor that you want to use, You want to use different combinations, but of course you studied the literature and this is where they come from, but you cannot exclude that somebody comes up with something even better.
Absolutely, absolutely. So my friend and collaborator Dmitry, who asked the question, refers to a previous title of my paper, which was the world's best nominal recursor. But in the meantime, I mean, the comparison is actually not even strict. So there is in this fauna of recursors, of connected recursors, there is room for improvement. So I don't have a maximality result of any kind. So it's even hard to say what it means for a recursor to be maximal, because this is something that I didn't get to discuss. You have different recursors, and they compare. This abstract view of recursors allows them to be compared with the expressiveness quite straightforwardly. So essentially, the closer a recursor keeps its extended category to its base category, the more expressive it is, roughly speaking. Because if you can move in an initial object preserving way between the extended categories, then you can simulate one recursor with the other. But I don't think there is a closest recursors there, so I don't think there is a most expressive recursor actually.
Thanks.
All right, so let's thank the speaker again.